Handouts are actually right there now, so if you haven't grabbed a handout, make sure to grab a handout. And good afternoon, welcome back to CS240. This is Intro to Computer Systems. And I want to get started exactly where we got left off, and that was a promise to talk about your dream computers. So for your very first homework, homework 0, we talked about the dream computer, and we're going to start navigating into the CPU as the second foundation to a computer system. So as we're navigating into the CPU, we're going to have to talk about the CPUs that you guys have chosen. So I have all of your responses here, but I actually want to hear from you guys about what you feel about your dream computer. So I just want to hear from a couple of you to kind of, do any of you guys have something you're loving about your dream computer that you want to share with everyone? Yeah, maybe? Either of you?
For like the chip itself, I went on like the M1 chip.
Oh. So you're thinking a new M1 laptop, right? Awesome. Who is on board with the M1 being your dream computer's chip? All right, M1 fan, M1 fan, M1 fan. Awesome. M1. M1. M1, another M1, M1. Awesome. So what do you love about the M1? What do either of you? You guys were the M1s over here?
It's like really fast.
Really fast? Okay, so you love the Mac more than anything is what I'm hearing, right? So it's both fast, but you also love the Mac, right? If you need a handout, handouts are right here in front of that door. So you love the Mac. What do you, other of you guys who chose the M1, do you guys, are you choosing it for the processor or for the Mac-ness of it?
I think it's more so because like Apple is making the chip itself, so they know what they need to protect the computer, so it's like very optimized.
Oh, so Apple's making the chip itself so they can integrate it with the OS, they can integrate all the parts of the system. I love it. What were you thinking?
Yeah, I was going to say the same thing. I love Mac OS, and because the chip is integrated with it, it makes like whenever I use a computer, way better.
So you love the full integration of it. The idea that, what is the M1? Do any of you, if you have an M1 chip, I think the battery life is what, like 15 hours or something? Say what? You say 15? Or I'm not actually sure, but I know it's crazy long hours because they're able to integrate like all the power supply management, all different components into a single chip. So that's interesting. So for you, those of you guys who chose an M1 chip, what instruction set architecture ISA was that chip? Any of you guys remember what the ISA for that chip was? You remember? No? Yeah. Yeah, it was ARM. So this is a completely different instruction set architecture than other chips. So for the rest of you guys, I'm guessing you guys did not choose an ARM chip, right? So what about any of you? What do you feel like your dream computer was? Any of you guys want to share?
Mine was Dell XPS 30.
Dell XPS, do you remember what processor was in it?
What processor?
Yeah, the CPU.
Intel i7.
Okay, so yeah, an Intel i7 processor. Do you remember do any of you guys also have an i7 in yours? No? What do you have in yours? Do you remember? Oh, you were an M1? Do you guys remember what you had in yours? Not really. So what about you guys? Any of you guys? Intel chips? Intel, AMD? Do you remember? Or Intel?
I put Intel.
You put Intel? Why did you choose an Intel chip?
So, well, I actually never used the Mac system until about 2 weeks ago. I got a MacBook. But I think I like the Mac better now, but I'm just a lot more familiar with Windows architecture.
Okay, so you're kind of a fan of Windows, and the Intel processors sort of are what you have to use on Windows. I think seeing in the spreadsheet, I think what I saw a few of you guys put was kind of powerful, anything you want to do. I think a number of you guys had gaming as kind of a dream computer idea. So that there's definitely a lot of kind of, if you're looking for gaming, you have an Intel chip with a lot of RAM. I think especially if we scroll down 16, I sorted this by RAM, so by the time we get down to like 64 gigabytes, powerful for loading and gaming. So you have this computer that you're using for lots of different tasks, particularly if you, for Windows, one thing that Windows generally excels at is Windows has an ecosystem that generally runs more games, at least historically, than like the Mac ecosystem. So that was a reason some people chose Windows. Somebody wants only half a gig of RAM. I think that may have been a mistake. So we have a number of different systems that people have built. So I want to think about what our dream computer is. So if I look at all of these, there is several different ARMs under instruction set architecture. There are several people who have an ARM computer, but I'm seeing more x86s and x64s. So I'm thinking as an average, even though we've got a few Mac users throughout this class, I think on average, it looks like we are still having an Intel processor inside of our computer. But we are definitely going to pay attention to the key differences between an Intel processor and an Apple Silicon processor. What's the difference between x86/x64 and ARM? How do these things differ? What advantages and disadvantages do we have between the two of them? Then we got to think about how much RAM do we have in our system. So if we look at the sheet, we have a few people at 128. We have a good chunk of people at 16 gigs of RAM. We have 32 gigs starting about here and moving down to about here. We have someone with 40 gigs, 64 gigs, 64 gigs, 64, 64, 64, and a few people with just 8 gigs. So I think the mode of this data set was definitely 16 gigs. But for our dream computer, should we just stick with 16 or do we want to stick an extra RAM in there? So whose team stick with 16? Whose team let's stick more RAM in there? Okay, should we go to 32 or 64? What are you guys thinking? 64? Works better? Any objections to 64? All right, so we have an Intel processor with 64 gigabytes of RAM that we're going to stick inside of our computer system. So I'm going to say our dream computer is going to be an Intel, and this is going to be an x86/64 processor. So we're going to have an Intel x86-64 processor, and it's going to have 64 gigabytes of RAM. So as we go through certain examples, we're going to look at this class dream computer. And this is going to be a lot of what our examples, but I'm going to pay a lot more attention to the Apple Silicon chip, because I feel like a good quarter of us are dreaming about the Apple Silicon. So I think it's really, and I think there's actually going to be more and more ARM chips out there. I wouldn't be surprised if Intel doesn't do an ARM chip before long. So I think that that's worth looking at. So that's our dream computer. So we're going to use this throughout the entire semester as we talk about computers and the architecture. So I wanted to make sure we had our dream computer because we're going to now navigate from just talking about data to actually talking about how the CPU begins to process the data. So last week was all data. This week's going to mainly focus on the CPU. And you're going to see that we're still going to have to use the knowledge we know about data inside of a computer to help us understand how a CPU works. So if we think about binary addition, we can add binary numbers just like regular numbers, except for we're in base 2. We only have zeros and ones. So when we go from the least significant digit all the way on the right to the left, if we have 1 plus 1, what happens? What do we get when we do 1 plus 1? Yeah, we get 1, 0. So we get a 0, and we have to carry a 1. Then we have 1 plus 1, which is, again, a 0 carrying a 1. 1, 1, 1, 0. So nothing scary about binary addition. It works just like decimal addition, except for you only have zeros and ones. I want to just make sure I'm not lying to you. So remember, this is your 1s, your 2s, the 4s, the 8s, the 16s. So 16 plus 2 plus 1 is 19, plus, this is 8 plus 1 plus 9. 19 plus 9 is 28. Let's make sure this is 1, 2, 4, 8, 16. So 16 plus 8 is 24, plus 4 is 28. 28 is equal to 28. So what we saw was binary addition works. Nothing, no problem here. So we can do another example. 1, 1, carry, that becomes 0. This becomes a little tricky because what happens when we do 1 plus 1 plus 1? What do we get? 1, 1. We got to have a 1 as the output and carry a 1. 1 and 0 is 1, 0, carry the 1. So what we see here is 3 plus 7 should be 10. This is an 8 and a 2, so this is 10, 10, and 10. We are good. So this works very well for positive numbers. But in computer systems, we're not just going to be dealing with positive numbers. So we're going to have negative numbers. And negative numbers, we're going to do something very clever. Because we are computer scientists, we are lazy. We don't want to do more work than we have to do. So as lazy computer scientists, let's say for negative numbers, we're going to use the most significant bit and when we say most significant bit, you're going to see a common abbreviation for that is the MSB, the most significant bit. So this is the bit furthest to the left. This is the bit with the highest place value, the most significant bit in the number. We're going to use the most significant bit as a sign bit. So the number furthest to the left, the most significant bit, is going to be our sign bit. And we're going to say that 0 is positive and 1 is negative. So if we look at a number and we set the leftmost bit to a 1, we say that that is a negative number. So we're basically going to have our numbers only go up to 1 power of 2 lower, but we're just going to say the very most significant bit is the sign bit. So if we do this, we can actually go ahead and say we can subtract numbers now too. So here, if I'm going to subtract a number, I'm going to add the negative version of it. So I'm going to transform this into 0, 1, 0, 0, 1, 1, the same number. But now I'm going to go ahead and swap the sign bit. So I'm going to say plus 1, 0, 1, 0, 0, 1. So all I've done is I've changed the subtraction to adding a negative number. And let's go ahead and add them together, going from right to left. 1 and 1 is 0, carry a 1, 0, 1, 0, carry a 1. Oops. 0, carry a 1, 0, 1. Wait, I think I screwed up my... Hold on. I wrote these numbers not aligned. All right, there we go. I get 1, 1, 1, 1, 0, 0. Is that what you guys got? Yeah, so aligning your zeros and ones are important. Okay, so I just swapped the most significant bit in the negative number, and then I can go ahead and add two numbers together. And let's see what this value is. So again, this was your 1s, your 2s, the 4s, the 8s, the 16s. So this was 19. Then minus, this was an 8, a 1, minus 9. So I expect to get 10. 10 is the answer I expect to get. Let's see what happens. So I know I'm doing 19 plus Negative 10 was what we said it'd be. So this should be, well, this 1, 2, 4, 8, 16. We said this last bit was our sign bit. So 16 plus 8 is 24, plus 4 is 20. Negative 20. Wait, is 10 and negative 28 the correct? Is that the same? No. So we have a problem here. If we just swap the sign bit, we end up in a situation where we have to make new rules of addition. So as computer scientists, we can decide what we want to do at this point. Do we want to create new rules of addition so we do binary addition with a different set of rules than we're used to? Or do we want to create a new way to store the number in binaries so we can use the regular rules of addition? And there's solutions doing both of them. What do you want? Yeah. Should it be what? Oh, should it be negative 9? Isn't it 19 minus 9? Oh, on the right side. Oh, yeah. Yeah, you're right. So, do we want to change the rules of addition, or do we want to change how we represent our numbers? What's your preference? Yeah. Change how we represent the number. Who agrees? What's your name again? Who agrees with Jackson? That we want to change the way we represent our numbers rather than changing the rules of addition? Does anyone want to change the rules of addition? Kind of want to see it. There are ways to do it. It's painful. I think I agree with Jackson. Let's actually change the way we represent numbers so that then we don't have to learn a new way to add. So again, the idea of systems is we want to make things as convenient as possible. So we want to develop techniques that use all of our existing knowledge and all of our existing resources so that we don't have to reinvent a wheel. So let's change the number system so we don't have to relearn how to add. And that is exactly the goal of 2's complement. And you can see this is also broken as well, the second example. But 2's complement is a way we represent a signed number, so a positive or a negative number, in a way that we can still use binary addition. So the entire goal of the 2's complement representation of a number is to create a system where we can use the same binary addition that we've known for all our lives, and it just works. So the goal is to create a system that just works so that we don't have to relearn how to add. And what's beautiful is the system that works is very, very easy. So there is one simple method that only contains 2 steps, that if you follow these 2 steps, you're always going to be able to get a 2's complement, or you're always going to get a number that you can just add. So if you have a negative number, so to convert a number to or from 2's complements. So to convert a number to or from, you actually can use the same steps to go to 2's complements or from 2's complements. It's the exact same rules. Step 1 is all I need to do is I need to flip all of the bits. So I'm just going to take my number, flip all of the bits, change zeros to ones, the ones to zeros. And the only other thing I need to do is the second step is I need to then add 1. So to go to or from 2's complements, I need to flip all of the bits and then add 1. That's it. So let's see this in action. So negative 17, I'm going to, and I think I should have probably flipped all of the bits of the positive number. Sorry. So step 1 is flip all of the bits of the positive number, just to make that explicitly clear. And then we add 1. So negative 17, we want the positive number of negative 17. So since we're flipping all of the bits, we have to decide what kind of computer we're on. So we could be on a 64-bit machine. That requires a whole bunch of zeros. So I'm going to assume we're on a 7-bit machine. So if we're on a 7-bit machine, that means every single time we write out a number, it's going to have all 7 bits in it. So the number 17, well, I need 116, no 8s, no 4s, no 2s, 1, 1. And then it's a 7-bit machine, so I need 7 bits. So negative 17, so positive 17, the positive number on this is 001, 0001. So that is 17 as the positive number. To convert it into the 2's complement representation, I need to do step 1, which is to flip all the bits. So step 1 is flip. So that becomes 110, 1110 by just simply flipping all of the bits. And then the second step is to simply add 1. So this is 110, 1111 is the 2's complement representation of negative 17. So we can add and subtract this 2's complement number just with normal binary math, and everything should just work. But I also said we can go from 2's complements back to regular notation by doing the same set of steps. So I'm going to repeat these 2 steps. I'm going to do step 1 to flip the number. So I can flip this number back. So 0010000, and then I can add 1, and I get 0010001. So if I have a negative number, I can follow the same steps of flipping all the bits and adding 1 to get back to my original positive 17. So these are the 2 steps you have to know for 2's complements. Flip all the bits, add 1. And notice when we look at a number, that most significant bit tells us that that is a negative number. Let's do this just a couple more times. So negative 4, well, the positive representation of negative 4 is 1, 4, no 2s, no 1s. So I get, on a 7-bit system, I get 0, 0, 0, 0, 1, 0, 0, 0. I'm going to follow my 2 steps. First step is to flip the bits. That becomes 1, 1, 1, 1, 0, 1, 1. Then second step is to add 1. So the 2's complement representation of this number is going to be 1, 1, 1, 1, 1, 0, 0. So that is negative 4 in 2's complement notation. And what I find really interesting is what happens with negative 1. So negative 1, positive 1, is simply equal to all zeros except for the least significant bit is a 1. If we do step 1 to flip all the bits, we get all 1s except for the least significant bit is a 0. Then we add 1, and we get all 1s. So negative 1 is actually all 1s, while 0 is all zeros. All right, so is everyone comfortable on how you can take a number and get its 2's complement's negative representation? So we went through all this whole process to learn a new way to represent numbers in binary, just so that we can make addition work. So now I'm going to go back to where we began and say, I want to do 42 minus 18. Yeah?
Let's say we have a number that in the 17-bit representation begins with a 1.
Oh.
Do we have to upgrade our number of bits?
Yeah. So if we have the number where we need that 7th bit, that number no longer fits in the memory. So yeah, if we don't have it, we need to either take like 2 words inside of our processor to store that number, like a long instead of an int or something. So yeah, we can't get around the fact that we need, if we have a 7-bit machine and we're using 2's complements, the biggest number we can store is actually just 2 to the 6th instead of 2 to the 7th. Yeah? Yes. Yeah, so is that why integer overflow works the way it does? And that's exactly why integer overflow works. So if you think about an 8-bit system, you can go all the way from 0 to 127, and then if you overflow 127, you loop all the way back around to negative 128. And that's exactly why it works. And it works that way because if you think about 127, 127 is 0, 1, 1, 1, 1, 1, 1, 1. If I add 1 to that, right, I'm now overflowing my integer. So I get 1, 0, 0, 0, 0, 0, 0, 0. And now this is a negative number, so I'm going to unroll it from 2's complement. So I'm going to flip all the bits. Add 1. And, flip all the bits. And if I add 1, I get, I get sort of back to where I am, but I end up with 128. If you, wait, why does, oh, right, because, sorry, yeah, I end up with 128 because I've added 1 to 127. I should get 128. I overload again, so I'm actually in an infinite loop. But you can see how that would end up at 128. Does that make sense? Yeah.
I think that helps me remember this is like, so if you want, like, if negative 17, then 17 is after 0.
Yes.
And if you flip the bits, like, and then add 2 numbers, like, well, if you add the flip, then you always get 1, 1, 1, like, all 1.
Yeah.
So plus 1 is that, is 0, all 0.
Yes. Yeah. And that's the kind of logic behind why 2 complements work. So that's exactly right. All right, but let's prove that this works. Let's actually see 42 minus 18. So 42 minus 18, I'm just going to do it in decimal first before we go crazy. So in decimal first, 42 minus 18, that's going to be 24, I think. So let's see if this actually works. So the first thing I'm going to do is I'm going to make a note of what is, so 42, that's going to be 32 plus 8 plus 2. So I need no 1s, 1, 2, no 4s, 1, 8, no 16s, 132, and it's a positive number, so my sign bit is 0. So that's 42. I'm going to get what 18 is in 2's complement. So I'm going to take 18, and 18 is going to be, that's 16 plus 2, so no 1s, 1, 2, no 4s, no 8s, 1, 16, no 32s, and right now it is a positive number. Step 1 is to flip all the bits. 1, 1, 0, 1, 1, 0, 1, then add 1. So negative 18 is 1, 1, 0, 1, 1, 1, 0. So if I do 42 plus negative 18, so plus what I figured out negative 18 was. So now I can add these 2 binary numbers together because I've got 42 and negative 18. And let's go ahead, 0 and 0 is 0, 1 and 1 is 0, carry 1, 1, that's a 0, carry 1, 1, 1, 1 is 1, carry 1, 1, 1 and 1 is 0, carry 1, that's 0, and we overflow a 1. So the resultant number is 0011000 in our 7-bit system. And we see that this is going to be 1, 2, 4, 8, 16. So 16 plus 8 is 24. 24, 24. This works out. The only thing we have to worry about is if we overflow a bit, we just have to drop that bit. We don't care about that overflow. We had to put something in the 8th bit, but we're only on a 7-bit system, so that overflow just goes goodbye. So even though the math has that 8-bit in there, remember we're just in a 7-bit system. We ignore the overflow. And you see, it just works. All right, let's do one more example of something simple. Let's do the exact opposite. So 18, well, we just said 18 was 0010010. And now we've got to figure out what negative 42 is in 2's complements notation. So we said that 42 was 0101010. We're going to use our trick of step 1, flipping all the bits, adding 1. So negative 42 is 1010110. And we add now this negative 42 to 18. And let's see what we end up with going from the right to left. 0 to 0 is 0. 1 and 1 is 0, carry a 1. 0, carry a 1. 1, 1, 1 is 0, carry a 1, 1, 1. So I get 1101000. So this answer that I get over here, is this a positive or a negative number? This is negative, and how do we know this? The most significant bit is a 1. So we know this is a negative result. So if I want to know what the positive number for this is, I'm going to go ahead and flip all these bits. Add 1, 0, 0, 1, 1, 0, 0, 0. And this is a 16 and an 8. So this is 24. So we know that this answer is negative 24. And what is 18 minus 42? Negative 24. So this just works, right? We don't have to reinvent addition. Instead, we just have to represent a negative number as a 2's complement notation. And in doing that, everything works. This is great. There's only one small caveat to all of this, which is actually getting back to a question I think you asked earlier about overflow. Negative 42 minus 32. What is this result in decimal? What's our correct answer? Negative 74. So we expect to get negative 74. Is there a problem creeping up? It's too large. Yeah. Negative 74 is getting a little big. We can't represent that in just the 6 bits that we have. So let's see what happens when we do this. So negative 42, we already have that from the previous one. So negative 42 was 1010110. We already know what that value was from the previous problem. Negative 32, well, that's a new one. Luckily, 32 is easy. That's a 0100000. So we just need 132 and nothing else. Flip all the bits because we know it's a negative number. So that's 101, 1111. Add 1, that becomes 110000. So we add 110000. So we have negative 42 plus negative 32. And now we use all the standard rules of addition because the CPU is a dumb device that's just going to do exactly what it's told. And it's going to say 0, 1, 1, 0, 1, 1, 0, 1 with the overflow bit. Simple addition, and we get a positive number out. We get a 32, a 16, no 8s, a 4, and a 2. So that's 20 and 32 is 52, 54. So positive 54, is that correct? No. 42 and 32, I don't even know how you end up with 54. So this is incorrect. Is it wrong because 2's complement is broken? No. Because can we actually represent negative 72 negative 74 in 6 bits? No, if we have that sign bit, the maximum number we can represent with just 6 bits is a 32 plus 16 plus 8 plus 4 plus 2 plus 1. So the maximum number we can represent is just the number 63, or negative 63. So negative 74 is too big. And this gets at the idea that one of the beautiful things about 2's complement is we have a way to represent overflow. We can find out whether or not our calculation overflows. So overflow detection requires us to just check 2 things when we look at the results of an addition. So when we're adding 2 numbers together using the 2's complement system, we get overflow. We have overflow if and only if 2 conditions are both true. So we have to have 2 things to be true to have overflow. The first thing is the sign bit of both inputs must be the same. So if we're adding a positive number to a negative number, we're never going to overflow because that's always going to be taking it closer to 0, right? If you got a positive and a negative, you're always going to get your answer closer to 0, so it's going to be an absolute smaller result. So the sign bits must be the same. You either have to be adding 2 positive numbers together or 2 negative numbers together. That's the only way we have overflow. The way we can detect overflow is we detect it by seeing if the sign bit of the result differs from the input. So we know we have overflow if we're adding 2 negative numbers together and the sign bit of the result is a positive number. Or if we're adding 2 positive numbers together and the sign bit of the result is a negative number. So to check whether or not our calculation is valid, we just got to check the inputs of the 2 sign bits and the sign bit of the output. And if we see the inputs of the sign bit are the same, and it's different in the output, we know we have overflow. We've detected that operation did not, that answer is garbage. So what's interesting is we don't actually care about the overflow bit that comes out of the math. That last bit, that 8th bit in our examples, we don't care about that. We're looking at only the sign bit, that most significant bit of the 2 inputs and the result. If these 2 statements are true, we have detected overflow in our addition. We can't represent the result in our current system. And this is going to be an important thing for the CPU to know. So the CPU is going to check whether or not the addition results in overflow. Cool. Any questions? Yeah.
Like, what does CPU do when it, like, when it detects an overflow?
What is CPU do when it detects an overflow? Usually set some register to say that there's an overflow. So it's going to set a bit that says the last operation you did had an overflow. It's going to be up to your program, up to assembly code that you might write, or the C code that you might check to see whether or not an overflow is there. So the CPU itself is just going to notify you there's an overflow. It's up to us to actually decide what we want to do about it. We may be totally okay with it, or we might want to do something about it. Cool. All right, let's just finish up this last example. Negative 31 minus 42. So negative 31, we'll go ahead and convert that to 2's complement. So positive 31 is going to be a 16, an 8, a 4, a 2, and a 1. Flip all the bits. Add 1. So negative 31 is 110, 0, 0, 0, 0, 1. Or I put too many zeros. 110, 0, 0, 0, 1 is negative 31. So I can go ahead and put negative 31 over here. That's 110, 0, 0, 0, 1. And then we know our good friend negative 42 is still, wait. Sorry, the last example is positive 30. Sorry. Positive 31 plus 42 is what I had on the paper. Sorry about that. So positive 31, let's just make sure the positive overflow works. So I was so excited about negative numbers, I want to keep them in there. So positive 31 is going to be 0, 0, 1, 1, 1, 1, 1. That's positive 31. Positive 42 is 0, 1, 0, 1, 0, 1, 0. We have from earlier. Just do simple basic addition. Let's see what happens. We have 1, we have 0, carry a 1, 1, or sorry, that's a 0, carry a 1, 1, 1, 1 is a 1 carrying a 1. That's going to be 0, carry a 1, 0, carry a 1, and a 1. So 31 plus 42 is 1001001. We don't even have to convert to figure out what in the world that number is, because what is the sign bit of both of our inputs? 0. And what's the sign bit of our output? 1. So do we have overflow? Yes. We have detected overflow. Sign bits are the same. Output sign bit is different. We know that that result is garbage. Let me go through the previous examples real fast to make sure that's true too. So here, sign bit negative 42 minus 32. Sign bit was 1, sign bit was 1 is the same sign bit. Output bit was 0. That is overflow as well. Going back to the example before that, 18 minus 42. The sign bit of 18 was 0. The sign bit of 42 was 1. So because the sign bits are different, we guarantee we don't have overflow. Because the sign bits have to be the same to have overflow. So you guys now know 2's complement. We can add and subtract negative numbers now. And we can do it using the same rules of addition we've always used. Because we have this clever way of representing negative numbers. Because we have the choice to either change the way we represent numbers or change the way we do addition. And I'm glad we chose to change the way we represented numbers. Because relearning addition sounds like not any fun. So any questions on 2's complement? I want to just briefly touch on multiplication. Let me know if I'm missing your question, because this room is I'm still getting used to this room. So let's talk about multiplication. Multiplication is fun. It's way more fun than division. So multiplication is pretty clever inside a computer. So 10 times 2. What is 10 times 2? Here we don't have, it's not a binary number. I'm not tricking you here. 10 times 2 is 20. Yeah. But now let's look at what is 10. So 10 in binary is, 1010. It has an 8 and a 2. What is 20 in binary? It needs a 16 and a 4. So 20 in binary is 10100. Oh. Interesting. All right. Let's do this again. 10 times 4 is 40. So 10 is still 1010. But 40 is, 40 is 32 plus 8. Oh, so we need 132, no 16, 1 8, no 4, no 2, no 1. Huh. Is there a common substring here? So 1010, 1010. So when we multiply by a power of 2, we actually just shift our bits. So this is times 2 squared. So when we multiply by 2 to the power 2, we can just shift our bits to the left by 2. So I'm going to say this was a left shift times 2. If we look back at what 10 times 2 was, that was times 2 to the first power. This was simply a left shift times 1. To the 9, 10 times 9 is 90. So the way computers usually think about multiplication is actually how can we get to 9 through adding multiples of power of 2. Because this is 10 times 2 to the third plus 2 to the 0th, right? So 8 plus 1 is 9, right? So essentially what this means is this is our binary number, 1010, and then we need to left shift it once by 3, so 3 left shifts, plus no left shifts. So if we want to multiply 10 times 9, well, we do some shift operations. And what we should see is through a shift operation and addition, we have the result of 10111010. I just want to make sure that this is actually 90. So I can say this is a 1, 2, 4, 8, 16, 32, 64. So I have a 64 and a 16. That's going to be 70, and an 8 and a 2, so 10 more. Or sorry, 80, I didn't carry. And we get 90. So 90, 90, it checks out. And this is sort of how a CPU thinks about multiplication. Is CPUs can actually do something really efficiently, and it can really efficiently shift bits around. So there's two kind of important operations inside of C. So you can do a left shift operation. And this is shifts a binary number to the left by n bits. So in C, we can actually do this by saying our number is shifted to the left by n bits. So I can say like int result is equal to shift to the left by n. So where is it? This left shift operator looks really, really familiar. Where have we seen these double carets before? Cout, yeah. So the cout operation actually uses a left shift operator, and it overloads that operator. So that is something that C++ can do, is you can do an operator overload. So it actually overloads the purpose of a left shift to actually allow you to stream something to the output. So it's kind of a clever use of how C++ overrides an operation that's not that commonly used in C++ code. So if you have streams, you can actually override that operator. Right shift does the same thing, but shifts to the right. So here we have int result 2 is equal to number, shift to the right by n. So shifting to the right is the same as dividing by a power of 2. So you're basically losing bits. It's chopping off bits because you're shifting it to the right, and the bytes that shift to the right fall off. So it may be useful to shift some bytes around, but it's useful to know that operation exists. Yeah?
Do CPUs usually have instructions for multiplication?
Yeah, CPUs definitely have instructions for multiplications.
Does it do it like sequentially, just shifting bits and adding?
Yeah, so how does the actual CPU do it? And for basic computations, like 10 times 9, it's probably going to do these things in parallel because there's lots of different things that happen in parallel. So it's probably going to figure out what the 2 to the third is and 2 to the 0th is. But then it'll just go ahead and do that all in parallel, yeah. So we'll actually look probably on Thursday about some of the CPU operations and how long it takes a CPU to do different operations. For example, if you're dividing two numbers, it takes about 100 times as long for the CPU to divide two numbers as it does to add two numbers. So the CPU can do a bunch of different things, but it takes different amount of cycles for the CPU to complete it. So we'll definitely talk more about that. Any other questions? Yeah?
So when we write shift, is the value of the lost bit matter?
It's just discarded. Yeah, so if I do, if I do like 10 right shift 2, then that's going to take 1010, chop off the last 2 bits, and that result is going to be 2. We just lose those bits. Yeah. Are there instructions for CPU? So division gets very, very complicated. And people have worked out how to do division with shifts and addition and subtraction, but it gets crazy. We're not actually going to cover division in this class. I don't even think they cover division in 233. You can work out the math and figure out how do you do division, but it's going to work fundamentally the same way. And integer division obviously works different than float division. Cool. Well then, for the last bit, I want to talk about logic gates. How does the CPU actually work? How do we actually design the CPU itself? And CPUs are actually designed by simply taking all these operations we've talked about so far and turning them into logical gates that perform the Boolean operations that we're familiar with. So by convention, we're going to think about things that have an input of A and an input of B. So we have input A, input B, and we're going to talk about gates that are going to combine 2 inputs into 1 or more outputs. So the first gate I'm going to talk about is the AND gate. So the AND gate is drawn with a straight line and then a curved output, and then a line that's usually called out. And sometimes people will write AND in the middle of that gate. So A and B comes into this gate, and we get the output from that gate. And we can talk about the truth table of any of these, which we've talked about earlier already. So if we have A and B, the output of the AND gate is going to be true only when both A and B are true. So this is the same as the AND operation we discussed on Thursday. So the output is true only if both the inputs are true. So if we have 2 bits coming into our processor circuitry, and they're both 1s, and when we think about these bits, what actually happens is inside the hardware, usually a 0 is considered low, and a 1 is considered high. And high might be like 5 volts of electricity. So you actually have electricity flowing through the high line. So when it's actually a 1, you've got electricity there. When it's actually a 0, you don't have any electricity there. So the AND gate's going to be some circuitry that actually only allows electricity through when both the inputs are on. But we don't just have AND. We've got our second gate, our good old friend, the OR gate. The OR gate also takes in 2 inputs, which we call A and B. And here we have a crescent-shaped input that kind of moves in a crescent shape to the output. So the biggest thing is the AND gate has that flat line. The OR gate has this crescent shape to create the output. And in this OR gate, we have the same truth table that we've seen for the OR operation on Thursday, where the OR gate is true when either one or both of the inputs are true. So if there's power on either A or B, there needs to be power on the output line. The third gate is the NOT gate. The NOT gate only takes 1 input in. So if we have A, the NOT gate is a triangle with a small circle at the end. And simply, if there's no power coming in, there should be power coming out. If there's power coming in, there should be no power coming out. That is the NOT gate. It's going to invert the status of that bit. And from here, what we do is we're going to take these 3 basic gates and start building more and more complex gates with those gates. So for example, we have an operation called the XOR operation. So I want to go ahead and take 2 lines of input, A and B, and I want to get A XOR B as my output. So we know XOR is if and only if exactly one of the bits are set, then we get a 1 on the output. So we don't already have a single gate to do that. So we're going to have to combine the gates we already know to get that. So this goes back to our 173 days to think about how can we use Boolean logic to develop an expression that we can then represent as gates. Because what Boolean expression in 173 terms of A and B is going to get the result of A XOR B without using the XOR? So I'm looking at, so this is going to be tricky. So if either one of them are true, that looks like an OR condition, right? So I think there's an A or B. Yeah. Yeah, and not A and B. So A or B and not A and B. So now we can actually represent this as gates. We can say, okay, well, this is A or B. And not A and B. So I'm going to go ahead and pull an A down and a B down and do, or sorry, A or B, sorry. A or B, here's the top, this is the OR gate, and not A and B, so I'm going to go ahead and do a not A and B, and then not it, negate it, and then these two outputs I'm going to bring together and do an AND gate to finish it up. So here's our inputs A and B. The top section is the A or B. Bottom section is the A and B, then taking the NOT of that, sending both of those outputs through an AND gate, and getting our final output. Do we ever want to draw all of these gates again? No. So, let's make a symbol for exclusive OR. So if we have A and B coming in, if we draw one crescent and then a second crescent for our OR, this kind of double crescent with that space between it, this is the conventional way that we draw an exclusive OR gate. So this is our good friend XOR. The beauty of this is we never have to draw all of these 3 individual gates or 4 individual gates again. We now have a representation to represent XOR, even though in hardware we know we might need 4 gates to actually build it. So we're basically building abstractions on top of basic logic for us to do more and more and more with an increasingly simple design. So we're abstracting away pieces of hardware. Yeah?
The same reason you should prefer the circuit over like A and not B or like B and not A.
So yeah, why use the math? Why use the circuit instead of the math, right? So certainly we can always think about things in either circuit or the math.
You could use different equations for like XOR, like A and not B, or like not A and B.
You're saying we could simplify this?
Or you can write the expression differently.
Yeah, we could.
Like, does it matter?
I mean, certainly doesn't matter from a pure, I mean, mathematically doesn't matter, no. From a hardware point of view, if we can do this with 3 gates instead of 4, that might be cheaper. So there may be ways to optimize this design. And we might be able to simplify expressions, especially when we get these really complex expressions. So are there ways to make cheaper hardware through math? Definitely. You can definitely use math to figure out how can you simplify a design. But ultimately, as long as all of the math is true and all of the gates are correct, the output should be correct, no matter how you design the circuitry. But there's ways you can optimize that optimize the circuit. Great question. Any others? All right, then let's actually start going. So there's one last thing I want to kind of mention just as an aside, which if we look at gates, there's something that computer architects care a lot about, this idea of what are the functionally complete gates? If you wanted to build an entire system out of just one gate, can you build an entire system out of just AND gates or just OR gates or just XOR gates? And the answer is actually no. So none of these gates are functionally complete. Because the idea is if you only have like a system that's off, that system just have low input, you never actually get a high input from these, from AND or not. So the classic functionally complete gate is people really love the NOR gate, A, NOR, B, so not OR. So this is just 1, 0, 0, 0. NOR is a functionally complete gate. It's just kind of a random aside. So if you talk to computer architects, they are kind of obsessed with the NOR gate, because the NOR gate, you can build every single circuit inside a computer using only NOR gates. So you can combine NOR gates just to build an entire computer. So this is a fun bit of trivia. NAND actually works as well. So NAND or NOR, they're both functionally complete gates. As computer scientists, we more think of AND, OR, and XOR being kind of the things we think about more naturally. So this is why I usually express things in AND, ORs, or XOR gates, but you can always convert between different types of gates. But and all of this stuff that we're learning about, this is stuff you can buy in hardware. There are hardware schematics. So this is the 4001 chipset specification. So you can download from Text Instrument this spec sheet. This is the spec sheet for the 401 chip. This 401 chip, it has a design. This particular chip has 4 NOR gates. So you can notice that this is, you can see it's got the OR gate, but it's got a little circle right here. That's going to negate it. So this is how you write a NOR gate. So this has, all the green ones are inputs. So you have 8 inputs for 4 outputs. This does 4 NOR gates on a single chip. And then the 2 red lines are giving it power. So if you're actually building a computer, you can buy this chip from TI. They're about 20 cents a piece. And this will give you 4 NOR gates in a single chip. And you can, sometimes the spec sheet are done by the layout of the actual physical circuit. Sometimes it's done more logically, where you have a beautiful layout and then you see numbers that label which pins it's on. So this output is pin 3, pin 4, pin 10, pin 11. That corresponds to pin 3, pin 4, pin 10, and pin 11. So depending on how they do the layout of the circuit design, you might see it as actually pin designed. You might see it as a pretty, as a design that looks prettier for an engineer to understand, but maybe not pin designed. And the actual physical chip just looks like a black box. So this is actual hardware. The only thing we've abstracted away is we haven't talked about the physics of how this actually is done, how you actually flip a switch when electricity is done, how you actually build a capacitor, or how you actually build a circuit and a capacitor and all the individual bits that make up these things that we call transistors. I'm going to link a video in the email I sent today if you're interested in kind of learning more about that process, kind of what is the physics behind it. I'll link that, because we're not going to talk any lower level than this. We're just going to say that these are gates, these gates make up chips, these chips make our computer run, there's a bunch of physics behind it, we're going to skip over all the physics. So I want to get us to the cloud. I want to start building amazing software. So let's talk about where we started today. Let's talk about binary addition. So binary addition done inside the computer is done by first having a half adder. So a half adder is going to be a simple piece of circuitry that's going to add 2 inputs and provide the output. So the goal of a half adder is to add 2 inputs together. So I'm going to go ahead and build our truth table for this. So all the possible values of A and B, well, we could do 0, 0, 0, 1, 1, 0, or 1, 1. And let's just think about what A plus B is. So moving down, that's going to be 0, 1, 1, 1, 0. So when we output from a half adder, we're going to output a sum bit and a carry bit. So what is the result of the sum? What's the result of the math? And what's the result of the carry? So the sum bits are going to be 0, 1, 1, 0. And then the only carry is going to be that very last row when both A and B are 1. So this is a truth table for a half adder. That sum column, what does that sum column look like as a gate? Yeah, that's an XOR gate. So this is A XOR B. And what does that carry column look like? And, yeah, this is A and B. Ooh. Okay. So now we can actually build a circuit. We can have an A and a B, and we know the sum bit is a result of an XOR, so I'm going to go ahead and build an XOR gate right here. And we know that the XOR of these, is the sum. And if I take an A, and I take a B, and I drag it down to an AND gate, we know that is the carry. So by using 2 gates, and remember the XOR gate's actually a complex gate, that actually has 4 gates inside of it. So we're abstracting away. And do we ever want to draw this thing again? I hope not. So if we never want to draw this again, what we're going to do is we're going to abstract this whole thing away and say that this whole thing is now a black box that I'm going to call an HA, or a half adder. A half adder takes in an A and a B and produces a sum and a carry. We don't care how it does it. We just know it's going to take in an A and a B and it's going to give us a sum and a carry out. And now we can always have this half adder that we can just use as a component that has 2 inputs and 2 outputs. But half adders don't really let us do very much. Because when we actually do addition, we have this annoying carry bit that came from the previous operation. So a full adder is going to allow us to add 3 bits together and produce output bits. So a half adder adds 2 bits together. A full adder adds 3 bits together. You have a question? No. Okay, cool. So the 3 bits that we generally think about for a full adder is we think about the A bit, the B bit, and the C in bit, the carry in bit. So the carry bit from probably the previous operation, and then a sum and to the carry out bit. So I'm going to go ahead and say, let's look at all of these with the carry in bit set to 0, and then them all set to 1. So I'm going to basically look at the A as 0, 0, 0, 1, 1, 0, 1, 1, and the A is 0, 0, 0, 1, 1, 0, 1, 1, when we have the carry bit both set to 0 and the carry bit set to 1. And then I'm going to figure out what is the sum of A, B, and C. So sum of 0, 0, 0, well, that's going to be 0 with no carry. The sum of 0, 1, 0 is 1 with no carry. Sum of 1, 0, 0 is 1 with no carry. Sum of 1, 1, 0 is 0 with 1 carry. Sum of 0, 0, 1 is 1 with no carry. 0, 1, 1 is 0 with 1 carry. 1, 0, 1 is 0 with 1 carry. And 1, 1, 1 is 1 with 1 carry. So now what we have to do is we have to figure out what is the circuitry to get A, B, and C into sum and carry out. If I look at how I calculated the sum, I literally just sort of added the 3 bits together, right? So what we're going to do is I want to leave you with just a little bit of a puzzle for you to kind of puzzle on your own. Because I think this is a really fun experiment and experience to do. Is can you use half adders? Think of only in terms of half adders and potentially like one other gate or so to create the sum and carry out column. What things do you need as inputs into your half adders to get the results of sum and carry out? What is the circuit you're going to build? So before lecture on Thursday, just work out what circuit can you build to get that actual output and try and use 2 half-adders to do it. And we'll talk more about this as the first thing on Thursday. We'll finish up this discussion of circuitry. Then the end of this discussion, we are done with circuits, and we're going to move on to how the CPU actually does stuff. So I'll be here if you have any questions. I'll have office hours right after this class. Otherwise, have a fantastic couple of days. I'm on both the Campus Wire and Discord sort of answering questions. And I will see you guys on Thursday.